Hello and welcome to this video that goes through some non-uniform moments questions. So we're going to use this worksheet that has been sent in. So question number 1, a non-uniform rod AB of length 4 meters and weight 6 newtons rests horizontally on two supports at A and B. Given that the center of mass of the rod is 2.4 meters from the end A, find the reactions at the two supports. Okay, so first of all we're going to draw this question out. So we've got our rod. We know that the length, so again it tells us that here it's AB and it is 4 meters long, and a weight of 6 newtons. So we're just going to put weight equals 6 newtons. Now the reason why we're not putting the weight in straight away is because it's a non-uniform rod, although later in the question it actually tells us where to put it. It rests horizontally on two supports at A and B. So we put the supports in at A and B. Given that the centre of the mass of the rod is 2.4 meters from the end A, so that tells us that here 6 newtons, and that is 2.4 meters. Find the reactions at the two supports. So we've got a reaction at A and a reaction at B. So that's our setup. And first of all, we assume that this is in equilibrium. So we're going to assume that the upwards forces equals the downwards forces. So the upwards forces here is the reaction forces at A and B go up, so it's going to be A plus B as both those going up, and the downwards force is equal to 6, which is the weight that's going down. From here we're going to take moments. Again, you can take moments from any point A or B, because we don't know either of them. I'm going to take moments from A. The reason why is because we know the distance directly from A to both of the other forces. So we're going to take moments from A. When we take moments from A, we determine which way goes anti-clockwise and which way goes clockwise. So again, we take A as the center of our clock and we determine which way they go round. So the 6 newtons one goes clockwise, and B is the anti-clockwise one. It goes upwards and around if we take A to be the center of the clock. So that is the anti-clockwise. Then our formula is moments equals force times distance. So I meant B for this one. So B is going round. So here, when we're doing this one, the force going anti-clockwise is B, and that is 4 meters away from A. So B times 4 is equal to the clockwise force, which is 6 times 2.4. And then all we need to do is just rearrange. So B is equal to 6 times 2.4 divided by 4, and that gives us our answer. So in the calculator, 6 times 2.4 divided by 4 gives us an answer of 3.6 newtons. Once we've got our answer for B, we can go back to our first equation we made, which is A plus B equals 6, and we can substitute our answer back in. So A plus 3.6 is equal to 6. And then from here we can say that A is equal to 6 minus 3.6, which is equal to 2.4 newtons. And that's our final answer for part 1. Question 2, a non-uniform bar AB of length 5 meters. So we're going to draw on one. Again, A, B, and then a length of 5 meters. Is supported horizontally on supports A and B. So again, we've got supports at both A and B. The reactions at these supports are 3G and 7G respectively. So 3G is here, 7G is on B. Find the position of the center of mass. So here we've got the weight acting down, and we're going to define. So here it doesn't define anything, it doesn't tell us anything, so we can make a decision of how we can set up our question. So here I'm going to say that A is X meters away from W. Again, I don't know, you could do the same, you could do a distance between the weight and B, but it's good to put some distance in. Then from here, again, we do the same setup as always. We do up equals down. Assume always that we're in equilibrium, unless stated in the question, although at this level it will most likely be in equilibrium. So the upward forces is 3G and 7G, and the downward forces equals the weight. So immediately we can say that the weight is equal to 10g. And then we're going to take moments. So we know moments is anti-clockwise equals clockwise. Because I've defined x to be from A, I'm going to take the moments from A. So here we're going to take moments from A. The weight will go clockwise around A. Again, take A to be the center of the clock, and W will go clockwise around it. And 7g will go anti-clockwise around. So we're going to put 7g over here. Again, our formula, moments equals force times distance. So in this situation, we're going to have 7g times 5 is equal to W, which is 10g. So 10g times x. And then all we can do is we can then rearrange, so it becomes 7g times 5 divided by 10g is equal to x. Obviously here you don't need to put g straight in the calculator because it cancels out. So essentially we're just left with 35. So 7 times 5 divided by 10, and x is equal to 3.5 meters. And that's your answer to question number 2. Okay, I'm going to clear the board and we'll move on to question 3. So question number 3, a non-uniform plank AB of length 4 meters and weight 120 newtons is pivoted at its midpoint. Okay, so this one a little bit more difficult. So again, we're going to define A and B. We know that the weight of the plank is equal to 120 newtons, and we know that this length here is 4 meters. So the length of the plank, it is non-uniform and it's pivoted at its midpoint. So we're going to put the pivot in here. The plank is in equilibrium in a horizontal position with a child of weight 200 newtons standing at A. Okay, so we're going to put the child, we always model this as a particle, and it's going down at 200 newtons, and a child of weight 300 newtons sitting at B. So we've got now a second child here, 300 newtons at B. And we know as well that because this is the midpoint, this is going to be 2 meters, because it tells us in the question that it's pivoted at its midpoint. By modeling the plank as a rod and the 2 children as particles, find the distance of the centre mass from A. Okay, so we're going to take the distance of the centre mass from A. So here we're going to say that this is 120, and we're going to say that this is some distance x away from A. Again, it doesn't matter where you place 120 newtons, we don't know where it is lying at the minute. So in terms of any forces acting on here that we've not included, again, we've got the pivot point, which will have a reaction force that goes upwards at that point. So how do we do from here? So the first things first is that we take our up and we take our down forces. So up is equal to down. The upwards forces here is just the reaction force, and the downwards forces is equal to the 200 from child A plus 120 from the weight of the plank plus 300 from child B. Those are all acting down. So that tells us immediately that the reaction force is equal to 620 newtons. Then the next thing we do is we're going to take our moment, so anti-clockwise equals clockwise. So here, because it wants us to measure our moments from A, our distance from the centre mass from A, I'm going to take moments from A because I'm allowed, basically, there's nothing stopping me here. I know all the distances and I know all the other forces, so it makes perfect sense just to make our question easier. So here the first thing we've got is our weight. Our weight is going clockwise. Our reaction force though is going anti-clockwise, and our 300 newtons is going clockwise. So from A, again, we ignore what's happening at A. When you take moments from a particular point, you ignore any forces that are acting at A. So the 200 newtons force in this particular situation, we ignore because it's not causing a turning point if we were standing at A, because it's acting at that point. So then from here, we use our formula, moments equals force times distance. The reaction force, so R is 620, so it's going to be 620 times 2 meters, because we're 2 meters away from A. And that's equal to the weight, so the weight is 120, so it's 120 times by x, so 120x, plus 300, which is 4 meters away from A, so it's the other end of the plank, so 300 times 4. From here, we'll just do a little bit of tidying up. So we've got 620 times 2, which is 1240, is equal to 120x plus 1200. And then from here, we're going to subtract that. So it's 1240 minus 1200 is equal to 120x. And then from here, we can say that this is 40 equals 120x. So 40 divided by 120 is equal to a third. So x is equal to a third meters, which is quite close, or 0.33 meters. And just double checking, so that is correct. So by 4, by 2, yeah, I think that is correct. Okay, so now we're going to move on to our next one, which is question 4. So a non-uniform rod of AB of length 5 meters and mass 15 kilograms rests horizontally suspended from the ceiling by 2 vertical strings attached to C and D. Okay, so we're going to have a rod here, so it's A and B, has a length of 5 meters and a mass of 15 kilograms. So we know the mass is 15 kilograms, so that gives us the weight, which is equal to 15g. Rest horizontally suspended from the ceiling by 2 vertical strings attached to C and D. So we told that AC is 1 meter. So it's going to be a string that goes upwards, and this is going, now here the string is pulling up on the rod, so therefore we take the force as going upwards because it's a string and it's holding it from the ceiling. So it acts as upwards force on our rod to keep it from falling down. And then we've got, so this here we know is 1 meter away, and we have AD, which is 3.5 meters, so another string at D, which is 3.5 meters away. So this is D, and this is 3.5 meters. Given that the center of mass is at E, where AE equals 3 meters, so we're given here that we've got another one, which gives us a different color so we can see. So here we're going to have our center of mass, which is going to be 15g, and this is going to be 3 meters away. Find the magnitude of the tensions in the string. Okay, so this one, first of all, so this is our setup that we got from the question. First of all, we do up equals down. So our upwards forces, remember in this question there's nothing happening at A and B, it's just telling us that's the rod. So the strings are only acting at C and D. So we've got force C, force D, that are acting upwards, and the only other force is acting downward, which is the weight of the rod, which is 15g. From here, we're going to take moments, so we've got anti-clockwise equals clockwise. And from here, we're not going to take it from A and B, we're going to take it from one of our unknown forces, C or D. So we're going to take moments from C. So moments from C. Okay, so first of all, determining the direction that they go. So going anti-clockwise around C, remember that's the middle point. So C is going, it's going to be 15g. So going clockwise is 15g, and going anti-clockwise is D. So that's going around, up and around C. And the next thing we need to determine is the distances. So from here, there's no direct measurement between the distances, so we need to work it out. So to get to D, so it's going to be D times, and here we know that the distance from A to D is 3.5 meters, but we know that C is already 1 meter away, so therefore we just do 3.5 minus 1 to give us our distance from C, which, well, give a distance between C and D. Because that's where remember we're taking moments from C, so it's the distance from C that we're measuring, not the distance from A. So here we measure that this distance here between C and D must be 2.5, so it's D times 2.5 is equal to 15g, and again we know that in the question it told us that it's at this point here, E, which is 3 meters away from A. We've already travelled 1 meter away from A to get to C, so between C and E must be 2 meters. So it's going to be 15g times 2. From here we can solve, so it's just going to be D equals 15g times 2 divided by 2.5, and therefore we can plug in our answer. So 15 times 2 divided by 2.5 gives us an answer of 12g. So D is equal to 12g, and then from here we can just plug that straight back into our answer. So C plus 12g is equal to 15g, and therefore C is equal to 3g. Again, it doesn't ask us, so we can most likely leave our answer like this. However, if you want to get a full number, we then plug in our answer. So 12 times 9.81, which is equal to 117.72 newtons, and 3 times 9.81, which gives us 29.43 newtons. Okay, if we look at part B, when a particle of mass 10 kilograms is attached to the rod at F, the rod is just about to rotate about D, find the distance AF. So this one we're just going to redraw it just quickly, because there's some big changes that happen at this point. So again, we've got points. So here, what the big difference is that now we're rotating around, we've got our points, and our points are D, C and D. We've got our weight that acts downwards, which was 15g, and now we've got some particle we're going to say here as x, and it's going to be 10g because it's got a mass of 10 kilograms, so the force acting at that point is 10g. Now what is interesting here is that it tells us that it's about to rotate about D. So remember that this is C, this is D. So if it's about to rotate about D, that means that C is actually equal to 0. So the force at C is equal to 0 when it's about to rotate at D. And this is because that the 10g force is pulling it round to rotate, therefore that there's now almost no force going upwards at this point, because of the fact that this bit at D is going to rotate around. So therefore we can see the force, there's no tension acting on that rope, the rod is almost moving upwards. You can think of it as like taking the string will now become slack, or just about to become slack, which means that it no longer has any tension in it. If you were to, for example, if you were to imagine holding your pen, and then if you were to hold it as it is in almost like an equilibrium as a straight bar, you have to apply some force upwards to hold it. As soon as you push down on it, you are no longer applying any force upwards to hold that pen if you're pushing down on the other side of the pen. And that means that sort of explains why at C, at that point, that the string or the rod, the vertical string at that point has no force, because the 10g, our additional one, is rotating around a specific point. So therefore so essentially that's why we take it as the force, the tension here is 0. And I'm not sure if that is still in the specification, but it's something that it's worth knowing, essentially, if it's so if you're going to take a point, so if you basically, in most of these situations, would be a string. If it tells you that it's going to rotate around one of the strings, then you can take the other string as equal to 0. The same with a support. If it tells you that it's going to rotate, so for example, an easier way to think about this in terms of like the opposite direction, if you've got C and you've got D here, if you say, oh, it's going to rotate about this point here, and it's just about to rotate around, that means that at D, if it's going to rotate, the plank is just about lifting off from D, so therefore there's no reaction force at D because it's about to rotate, it's about to move upwards. So that's why essentially at this point here, if it says it's about to rotate around C, then you would say that if you had a reaction force D, D would equal 0 here because the beam is about to lift off from the support. So that same concept, but flip it around this time, and instead the string that is holding it there now no longer needs to hold it there because the rod is about to move upwards due to the addition of the moment of the 10g force. So from here, this makes our situation quite straightforward, because now we can just take moments about D. And if we go back to our previous example, we know that E, which is the point where the weight is acting, is 3 meters away, and D is 3.5 meters away. So therefore, we know that this distance here is just 0.5 meters. We know that this is x, so all we then do here is we just say anti-clockwise equals clockwise. So this goes anti-clockwise, which is our 15g, and this goes clockwise, which is our 10g. So 15g times 0.5, from moments equals force times distance, is equal to 10g times x. And then we just rearrange, so it's 15g times 0.5 divided by 10g is equal to x. So 15 times 0.5 divided by 10, so x is equal to 0.75 meters. But now we need to go back to the question, and the question states find the distance AF. Well, here the distance from A to D is 3.5 meters, so we need to find this additional one here, which is what we've just done, which is x. So therefore A to F is equal to 3.5 plus 0.75, which if we plug in the calculator is equal to 4.25 meters. And that is the end of the question for 4B.